Everybody's weekend.
No.
Especially not after Friday. Yeah, right? Eat that every weekend. Yeah, that'd be nice. So announcements as we get started. I don't quite know about exams yet. Haven't seen the TA since Friday. Hoping I see him today. We have a meeting at noon anyway. So I'll get things figured out then. We have an assignment due on Wednesday. So it is probably worth getting started on that. We're trying to keep these a little bit smaller and more manageable, but that said, it's still reasonably sized. So I recommend getting started sooner rather than later if you have not yet. As for content, we're doing our last push through the pumping level. So this was the last example we covered last week. We wanted to show that this language is regular. And I'm hoping at this point, the process for the pumping lemma is starting to become a little bit clearer. So the first thing we do is we pick a string that is in the language with length at least m. And so for this, we picked ab to the m plus 1, a to the m as a good string. We needed n to be greater than k, strictly greater than k greater than or equal to 0. We wanted to make sure that we had within those first m characters at least continuing to repeat a's and b's. And that way we could break this down into some cases. We knew that the parts of the string x and y getting up to this loop happening within the first m characters, this cycle, I should say, and completing that cycle happens within the ab to the m plus 1 characters. This is because that can only last up to the first m characters, and the first m characters have to be within this portion of the string. So because of that, getting to the loop and completing the loop cycle has to be within those characters. And now we get back to, if we're playing the game, player 1, but what we need to consider for every possible breakdown now of y, how could x and y be broken down such that we end up with a legal case for x and y? We have 4 cases for this. We said they could start with an A, end with an A, start with an A, end with a B, start with a B, end with an A, start with a B, end with a B. And we found that the starts with an A, ends with an A, and starts with a B, ends with a B broke the structure of the string if we duplicated it. So we would set I to 2 if we did this, and we would see, we would repeat A, B, and at some point we'd have something like a Y that is A, B, A, or just A. And you repeat that, you get 2 A's in a row. And nowhere in that A, B to the end do we allow for consecutive A's. Similar for consecutive B's. There's another way to do it. You could just get rid of it, and then you end up with consecutive of the other character. If we end up with Y being starting with an A, ending with a B, or starting with a B, ending with an A, then again, we choose I equals 0. We don't go through that cycle. And that takes out at least one A and B from the string, which means that we can now go back to the n is strictly greater than k part of this language and show that that no longer holds. Because when we select the string ab to the m plus 1, a to the m, we're right on that decision boundary of if we subtracted a single AB from the first part of the string, we would have broken the n is greater than k condition. So whenever you're picking strings, try to pick one that's right on that decision boundary. And we continue this line of thinking for the 4 different cases that y could be. Were there any questions on this example, a more complicated example where you break them down into cases and then show that for each of those cases, there exists an I such that when we pump that, we end up in a final state, but have a string that should not be accepted. And that will always be the case. We want to show that there is a way to get to that final state such that we shouldn't be accepting the string. been a little bit since we talked about pumping lemma, so I just kind of want to query the class. How are we feeling about the pumping lemma at this point? I fully expect it to be somewhere like here. And that just shows that we need more practice. And I think that it is good to start with that practice and some homework, get stuck, come to office hours. But before we completely move on to a new topic, I want to talk about some pitfalls that you might run into while you construct these proofs, some common issues that I see. First one is trying to show via the pumping lemma that a language is regular. In fact, we cannot do that. So even if we could show that there is no string in the language that could ever be pumped out, it's not enough to show that the language is regular. We can only ever show it to prove that a language, use it to prove a language is not regular. If you start with a string that's not in the language, or start with a string that is not greater than or equal to n characters. An interesting example of this would be something like, the language is a to the n, such that n is a prime number. A string that you might decide to choose for this is, all right, let's set w equal to a to the m. Why can't we do this? Yeah.
Because if you have like n equals 3 for like a, and then you have 4 states, 4 would be prime, so you take 4.
Yeah, there's no guarantee here that m is prime. There is no restriction that we ourselves have placed on m. We just say, given m, let's say that w equals a to the m. And it may be that a DFA that represents and can recognize every prime number has a non-prime number of states. So instead, you would have to do something like, all right, we need the string to be prime. So let's say now that we will use m plus k, where k is whatever number is needed to go from m to the next prime number. And now we know that the string that we've given is actually in the language. It's actually prime. So now we know it's both greater than or equal to m and prime. Also some assumptions about how x, y, and z are decomposed. So we could say, same problem as above. We want to say that we're trying to figure out prime numbers. Given m, let w equal a to the k such that k is odd. Then we could move on to say subtracting an odd number of a's from a prime number means that xz without the y, since y was an odd number, has an even number of a's and cannot be prime. What are some issues with this proof?
You don't even have n, right? Or given.
Given m, yeah, we're going to say w equals a to the k such that k is odd. Multitude of issues here. There's no variable m anywhere in this, right?
Yeah.
There's no guarantee that k is prime, given that k is odd. If we wanted to say something like, all interesting prime numbers are odd, since it's going to be greater than 2, unless it's the 2 case, maybe we can split this into 2 cases, the 2 case and every other prime number is odd. Even if you did that, subtracting an odd number of a's from a prime number could bring you to 2, which is also prime as the even prime. So xz could be a character and a character, and you end up with a string that is prime, but it's even length. So it's just a bad idea to make the assumption k is odd in the first place. We don't know that for sure. And nothing about it being odd says that it is prime. None of this has anything to do with the string length m, the number of states in the DFA m. So we don't know whether a to the k has fewer than m characters in it. It is possible that that's the case. For our odd numbers, it would be less than the number of states in the accepting DFA. So some of these strings are acceptable and some of these are not. Additionally, things I've seen since I wrote this slide, instantiating m is a terrible idea in a proof. Please don't do it. If it helps you to understand the structure of things and help you to visualize, that is absolutely okay for you to do on scratch paper. But a diagram of a DFA with some number of states in it should not be in your proof and should not be in any pumping lemma answer to a problem, because we don't know that size. If you instantiate that size, even if you go through all of the work that is necessary with the pumping lemma, you're going to end up with, there is no whatever number you chose state DFA for this problem. If you chose 9, m equals 9, then you would have proven that there is no 9-state DFA for the problem, which does very little to say that there is no DFA of any size. You would have to show it for size 1 and size 2 and size 3 and size 4 and size 5 and size 6, etc. forever. You would never complete this proof, because just because you've gone up to size 10,000 doesn't mean there isn't a size 10,001 solution. Wherever you arbitrarily stopped that process, you just show that there is no DFA less than or equal to where you stopped that process. And we need to show that no such DFA can exist. And the only way we can do that is to carry m, the size of the DFA, all the way through the proof as a variable. What else have I seen? This is where I should have the TA come in here and tell me everything that he's seen on an assignment. Maybe he'll do that. Maybe I'll have him write something up. Questions about any pitfalls in pumping lemma proofs? Some of them will require you to think outside the box. There are a couple, even on this existing homework, that I think most people will probably want some kind of hint in office hours for. That's totally okay. But I throw it on there to challenge you and make sure I see you at some point if it's not readily apparent or intuitive. I'm happy to provide those hints, though, so don't feel like you're on your own, and I expect you to be able to do absolutely everything without any guidance whatsoever. Anything else? How can I help you feel better? One of the most challenging things in here, in case you don't already feel it. It's okay to feel like that. It's tough. Right. We'll move on then. A lot of the questions for pumping lemmas come out during the homeworks when you're working through them. So especially for this assignment, please do start today, get stuck today, and come get help. I'll be available in the early afternoons as well as my typical office hours for a good chunk of this week. All right. We've seen our first large language class, the regular languages, and we have completely gone through everything we care about with regards to regular languages. We've talked about how to prove them. We've talked about how to prove that a language is not in this class. So we're going to start talking about the next interesting class of languages, the context-free languages. So we just showed we can use the pumping lemma to show that a language is not regular. Why would we care about languages that aren't regular? It seems like regular languages are reasonably interesting and a good class of languages, but what about languages that aren't regular? Turns out there are many constructs that we use in programming and in the languages that we write that require a logic that can't be captured by this concept of a regular language. Let's take an example of this. A to the n, b to the n. We showed this language is not regular, right? Who remembers that proof? Now imagine replacing A's with left curly brackets and B's with right curly brackets. We have some way of now imagining some scope where we can allow for things like nested loops or conditionals in loops. We don't quite capture things like sequential with this. There's something that's a nested loop that has a loop inside a loop, but then there's sequential loops inside the outer loop. So we can't quite do that with this, but we can at least see some kind of nesting structure where we can have loops inside of loops inside of loops and a conditional inside of that innermost loop with something like nested scopes like this. So A to the n, B to the n is a useful language to capture nested scope. So if we want to be able to capture this reasoning in some kind of compiler, to be able to say, okay, I know what this programming language, what this program is doing, it's representing nested control structures, we need the ability to handle such languages. Something that allows us to reason about control. And in fact, we will see for most of the rest of this course how context-free languages are probably the most important class of language for a compiler. There are other important classes as well, but this is the main important class of language for a compiler. It does a lot for us. So we're going to spend quite a bit of time on it. With context-free languages, we don't start with the visualizer that we did before with the DFA and NFA. And the reason is it's quite a bit more complicated to put together a state machine for context-free languages. And in fact, we've already seen one such way of putting together context-free languages without realizing it. It was the first grammars that we talked about. So we'll start going back to the regular grammar. And who remembers what restrictions were placed on a grammar to make it a regular grammar?
It must be right linear, left.
Right linear, left linear, meaning that we have a sequence of terminals followed by a single non-terminal, or a single non-terminal followed by a sequence of terminals. And that had to be consistent across the entire grammar. We had to either have left linear or right linear for the entire grammar. So because context-free languages are a larger subclass of languages, that means that every regular language is also context-free. Regular languages are a subset of context-free languages. Every context-free language is also, every regular language is also context-free, but every context-free language is not necessarily regular. So many context-free languages that are not regular, but some that are. So we're going to lift the restriction of the non-terminal only appearing on the left or right-hand side of the production. And it's very similar to the first grammars that we saw. Here's an example context-free grammar. Go ahead and analyze the grammar and start with, what are some possible strings that are produced by this grammar? Once you have found a couple of strings that we accept and maybe a couple that we don't, try to figure out what language it represents. So going from, instead of thinking about the language and writing a grammar that represents the language, now analyze a grammar and try to determine which language it accepts. Does this look weirdly familiar?
War flashbacks.
What's the language?
So the strings in reverse, right?
Yeah, it's WWR. So string followed by that same string in reverse. We might ask, is it possible to produce this language with a regular grammar? I also asked this. And what did we come up with? It's not possible. It's good. It is not possible to produce. Why do we say that's impossible to produce before we go into further examples? What makes us or allows us to think that the language WWR is not regular by attaching itself to a grammar? Go back to that for a second. Yeah.
Because in order for us to represent WWR, we need to know beginning, like the end of the string in this logic, and for us to have a non-terminal at the end, that would completely destroy that logic.
Yeah.
Or at the beginning, non-terminal at the end.
Yeah, in order to do that, we have to be counting the length of W as we map this, the beginning to the end. The reason we have the non-terminal in the middle here is we can pair a character at the beginning and pair a character at the end. And we know that the first character is in W and the second character is in WR. And we know that for each one of these productions. As we construct a string, the character on the left, part of W, character on the right, part of WR. There's no way to factor that out to be able to say we can now have the non-terminal at the start or the end, because then we lose that knowledge of which characters come from W, which characters come from WR, so that we know where the middle is. So we need some additional power represented in our grammars to be able to make that distinction. All right, let's go ahead and produce a grammar for this language. A to the n, b to the m, such that n is not equal to m. Good example, I think. Both of them be empty. Yeah. It says nothing about whether, I guess, yeah, they can't both be empty because then n would be equal to m at 0. So yeah, we have to have at least one character. That is a great point. So for a structural representation of this, anyone have a hint or an idea of thinking of how to structurally break this down? What are the options for what these strings could look like? That's usually where I start when trying to construct a grammar. What is the overarching structure?
AA.
Something like AAB works. So the way that I want to break this down is there's some piece of this that is A to the, I can't use N or M because they're already used, but I'm going to use P standing for pairs, A to the P, B to the P. And there is either some A to the N minus P in front or B to the M minus P in the back. So we have a this or that, and we have this guaranteed in the middle. Does that structure make sense as to saying that they're not equal? There's an equal section in the middle, and either a non-empty beginning full of A's or a non-empty end of B's. I shouldn't say or, I should say an exclusive or. So we cannot have both. So maybe this helps you. Go ahead and finish this off. There's my full solution. I use the non-terminal P to stand for pairs. Each pair adds an A and a B recursing in the middle. We know that in the overall structure, the A's come before these pairs in order to have more A's than B's, and the B's would come after the pairs in order to have more B's than A's. So we're breaking this down immediately into were there more A's than B's or more B's than A's. The difference between them, we're going to figure out how many they are, that minus the, that tells you how many pairs there are, and then the difference, the either N minus P or M minus P as the number of times we'll take either the A's recursing at the beginning or B's recursing at the end. This actually doesn't matter where these are, they can be at the beginning, you can swap these, doesn't affect anything. I just like to think of recursing at the beginning to be able to say these A's come at the very beginning and the B's at the end, saying the B's come at the very end. But the way you choose to do that doesn't matter. Did we get something similar to this?
Can I ask if my solution is correct?
Yeah.
So I have S goes to A, capital A, or capital B, B. A, capital A, so now we're going to the next one.
Yeah.
Is going to A, capital A, or A, capital A, B. Or empty, lambda. And then B goes to capital B, B, or A, capital B, B, or lambda.
Interesting. So here we're saying I think this works.
It's like the same logic that you.
Yeah, you force, there's no way from A's to go to B's or from B's to go to A's. That would be the big thing that I'm looking for something that would be wrong, is the ability to produce some more A's in addition to A's paired with B's, and then somehow be able to produce some B's without A's. But since you have isolated that and the A's always stay in front of that, of all the B's, and the B's always stay behind all of the A's, in this case, the order is important. The B has to be here and the A has to be here.
Yeah.
But since they are, I think this works. Anyone see any issues with it? So as always with grammars and with state machines, there are multiple correct answers and multiple reasonings that will get you to a correct answer. Yeah, I like both of these. I can see the logic that went into both of them. Any other questions? I think what was here, I think that's similar to my solution. Yeah, that is my solution. But there are also other solutions. Is this what we had here? No, it's just the left-hand side of one. Ignore that one. All right. Here's another grammar. What language is accepted by this grammar? We'll go back the other way again. Any thoughts? What does this remind you of?
Is it? So I'm thinking, is it WWR squared?
It is not. It would be if we only allowed for a single SS,
Oh,
but that can recurse as well.
right.
So how I like to start this is I like to start with some derived strings. Just walk through this grammar and produce some strings that could be accepted. as an example, you could derive ABA, How could we get that string from this grammar?
If you go to essence, and then the first S becomes AB, goes into lambda, second it's just AB twice.
How could we get AAB? Does the first one make sense? Maybe we'll walk through the first one. So starting with S, we know we can at any point do an A and a B at the end and recurse in the middle. So since this starts with an A and ends with a B, we're going to do that. We're going to pick out that A and that B, and now S just represents the middle. Whenever we see two characters that are the same, the only way to generate that is going to be through SS. We need to do something that produces an A and a B or a B and an A in some capacity. And it turns out that, I guess, we have a BA here. So what would be missing here would be a BSA. We need the A's to come before the B's. So I actually don't think this can be derived with this. Unless we start with SS. Yep, and then we have to, from here, so restarting, we have to go SS. The A and B happens out front, and this A and B. So this S goes directly to AB. So A, S, B, S. This S goes to lambda. A, B, S. And this S goes to ASB. From there, and then this S goes to ASB. AB, A, S, B, B, and then this S goes to lambda. We end up with A, B, A, B, B. Very poor handwriting we got there. So that did not work. How do we get the bottom one?
Is that the one you were trying to do first? We first do S to ASB, the S and the just becomes.
Yeah, then we need the AB and the AB here. Yeah, so here we have S arrow. We start with the ASB. Recurse in the middle. This S has to become an SS. A, S, S, B. Now each of these become an AB. So we end up with A, ASB, SB. And this first S becomes lambda. So we have AAB, SB. And then this S becomes ASB, AAB, ASB, B, and then that S becomes lambda. A, B, A, B, B. Does that make sense? At least how that string gets derived? Come up with a couple more if you want to. Just come up with paths through this grammar that produce something. And then come up with, in general, what language is this describing?
Isn't it just A to the N, B to the N, or N grading somewhere?
But we can recurse in the middle and make a recursive A to the N, B to the N inside of it. So there's some recursive process to this and sequential process to it as well. We can either have an A to the N, B to the N. I guess it really is just a single one, but inside of that, we allow for what does this map to, especially if I hint that it's something related to programming and control structures. Anyone see something interesting?
Is it like
Yeah. There's one more string. What does A represent and what does B represent? They're not A's and B's. Yes, yeah.
Just whenever there's an equal number of A's
There are an equal number of A's and B's.
and
What do we know? What comes in equal numbers of
the curly brackets.
curly brackets and or parentheses? Both of those. Yeah. So this maps to legal mathematical structures or legal scope structures where we can have sequential scopes inside of another scope. This allows for that. So now we can do something like write a for loop that begins, and within that we have a for loop that begins and ends, and another for loop that begins and ends before this for loop ends. So this would be the equivalent of A, B, B. Which is that. We could also make a for loop that the first one closes right away before we get into the second set of nested pairs. Or we could make another one that is 3 consecutive for loops, that there's nothing inside of any of them, and that would map to the third one there. But there are more strings than that for 3 different loops, and you would have every possibility for how those loops could be sequential and or nested. So that's kind of cool. But it also works for math expressions. So that's also cool. Any questions on this idea or how this maps to some common programming language syntax?
when it says what language, I just automatically assume that it's something we want to express in set notation.
Yeah,
Do we just want to throw in just it could be kind of
yeah, we could absolutely do this in terms of set notation. So we need some subset of characters that are, if we wanted to do this in, what would we say? We have some expression. I'll come up with it and get it back to you. It would take me a couple minutes to do this in class, and I wanna do more with class. Last thing I want to cover is leftmost and rightmost derivations. So we'll come back to this idea of an ambiguous grammar, but we will start by saying if we can produce the same string via multiple different productions or paths through the grammar, then the grammar is ambiguous. I'll give you an example. Here is an ambiguous grammar. If I asked you to produce the string AAB from this grammar, number the productions in the order that you would, starting with S, and see if you can come up with a couple different paths to this grammar that can produce the string AAB. So something like this. Where I tell you which numbered production is used to derive the next set, the next production set. And then we're going to, from here, apply something else, some other number, and eventually end up with AAB. Try to come up with two different solutions to this, two different paths through this grammar. Excuse me. It's like, I think we're there. Let's give you a couple of them. You get something similar? So we can either go straight down the list, 1, 2, 3, 4, 5, or we can bounce around 1, 4, 2, 5, 3, and end up with exactly the same string. However, notice the ambiguity kind of goes away in this case if we force an order, if we're either going to replace the leftmost non-terminal or the rightmost non-terminal first. Whenever we end with this AB, we start with this AB here because we have to start with this production. The difference in this really was we're going to evaluate the A first, or we're going to evaluate the B first, and the path that followed through that was it's logically followed which of those non-terminals we decided to replace first. So if you continuously replace the leftmost non-terminal, we're going to call this a leftmost derivation. And if you continuously replace the rightmost non-terminal, we'll call that a rightmost derivation. So we can distinguish between the order in which we're evaluating non-terminals. We're going left to right or right to left. At every possible state here, we take the leftmost non-terminal and say, let's find something for that. Leftmost non-terminal, let's find something for that into lambda. Leftmost non-terminal is now the B, still the B, we have an answer. And now rightmost, we say find something for the B, find something for the B. There's nothing that could have gone for the B at this point, so we have to go to the thing on the left because no valid production could replace that at that point. So ambiguous grammars will come back to exactly why these are terrible. But since there are different ways that statements can be interpreted, that means that there is an actual branch or a tree that can end up having very different paths, and even for something like a compiler, interpreting the same code in different ways. You can imagine running your code once and getting one answer and running it again and getting another answer. That's scary. That is not something you want out of logic. But it's possible if there were ambiguity in how to read the rules of the language. So we'll come back and talk about this more tomorrow. I have office hours starting now for those who would like some homework assistance, and we just to work on it. I will see you shortly.